All right, we're jumping into section 14.8. So got this long awaited topic. So we're talking about change of variables, and then we're talking about, well, what is that scale factor that gets multiplied by the integrand? Where does it come from, and how do we know what it is? So its name, it's called the Jacobian, and we're going to talk about that in a minute. But to kind of motivate where it comes from, I want to just go back to thinking about single integrals. I want to think about when we do some sort of variable substitution. So maybe a U substitution, maybe a trig substitution. So something like a trig substitution, right, was when we did something like x equals sine theta. And if you remember then, what you get is when you do that, something like x equals sine theta, you also then had to figure out, well, what is dx going to be, right? It was g prime of x, and then, let's make this g of something else. So like g of u. So then what we're going to end up getting is something like g prime of u du. Right, so we're converting x into some function of another variable, right? Like when x was sine theta, well then we really had to sub in dx is cosine theta d theta. We end up with an extra factor in our integrand. So something like the integral from a to b of f of x dx becomes the integral, we change the bounds to something like c to d, where those bounds came from using the function to figure out what, how to make g equal to a and how to make g equal to b. And then we would do f of, well, we would replace all the x's with the function that we did, so like f of g of u, but then we replace dx with the entire expression, g prime of u du. The same thing sometimes happened when we just did something simple like a u substitution, right? Potentially once we've subbed over to du, we might need to change by a scale factor somehow. So we might end up altering our integrand in order to make that change of variables work. And it makes a lot of sense in those cases because really we're trying to go from a change in one variable to a change in another variable, which is related to those related rate derivatives. So it's natural then that the same idea is going to happen when we're doing double and triple integrals. So we're going to start with talking about double integrals. And the question is, well, how do I know what that scale factor is going to be? When it's just a single variable, well, it just comes from the derivative of whatever function you're letting x be. But now derivative is not as simple of a concept when you have multiple variable functions because there's multiple derivatives. So we're going to see how we're going to put them together. The scaled factor is called the Jacobian, which is named after a famous mathematician with the last name of Jacob. Fun fact, this is where Professor Pete has forever wanted to, the minute he took a Calc 3 course and saw the phrase Jacobian, he has wanted to name his child Jacob Ian. I doubt that we'll let that happen, but that was his joke and his dream from Calc 3, so I would be remiss if I didn't share that with you. But what we end up with, the way to find the Jacobian, because one of the things in the future is we're always going to have to always remember the Jacobian, don't forget Jacobian. What we're doing with this one is our change of variables is more complicated, right? We have to sub out x and y. And we're going to sub those out for two other variables, something like a u and a v. So we're going to have, say, x goes to g of uv, and y goes to h of uv. Then the way that we're going to define the Jacobian of x and y, so this is really for a double integral. This is like if I've got two variables and I'm switching to a different two variables. The Jacobian of x and y with respect to u is represented like this. We use that same partial symbol out front, so it's the Jacobian of the partial of xy with respect to uv. And the way that we do it is we set it up, remember this notation that we had in the past, this was that determinant notation. We used it when we did cross products. So we've got on the top row the two partials with respect to x, and they're in the order of uv. So this is dx du, so the partial of x with respect to u, the partial of x with respect to v, so those will be two expressions. And then in the second row, we've got the partial of y with respect to u, and then the partial of y with respect to v. And if you remember, the way that we compute this determinant form is you multiply on that main diagonal. So we've got the partial of u, so the partial of x with respect to u times the partial of y with respect to v, and then you subtract the multiplication of the off diagonal. So the partial of, so minus the partial of x with respect to v times the partial of y with respect to u. This factor is called the Jacobian, and what ends up happening is if I switch my integral from going from being in terms of x and y, so in terms of rectangular coordinates, to this new coordinate system in terms of u and v, well, my region's going to change. So it's going to go from some region R to some region S. I'm going to talk about that more in the next video. And then inside the actual integrand function, we would have to make those substitutions for x and y. And then that scaled factor that we're going to get is we're going to multiply by a factor of the absolute value of the Jacobian. So we're always going to take the absolute value version of it. And then that would be du dv. So what we're going to see in our next video, we're going to talk a little bit more about this idea of how to switch the integrals. What does it look like geometrically? And also we'll look at some of our old friends to see things like, well, what if we do like a change into polar coordinates? How does that relate back to this? So we'll jump onto that next video here.